Okay, so everyone, today I'll be doing the week 6 AMS quiz for physics. So first we start with question 1. Which of the following way actions would demagnetize a magnet? Okay, so using an alternate, this came in the periodic today, obviously. Using an alternating current in an electromagnet and dropping the magnet and storing the magnet in that soft iron keeper. Now, storing the magnet anywhere in any temperature other than like really really hot temperatures is generally fine. So obviously these two are gonna be wrong. Keep in mind it has to be with the iron keeper. That's like just general note. What are some common applications of electromagnets? Record head of the tape recorder, the relay, and the fire alarm bell. Now there's also the reed switch, I believe, and there might be the. I think that's it. But they might give you another one. However, these are you check from the book, but I'm positive they're gonna bring this copy paste. I have no idea what a four diode bridge rectifier is or a time delay switch, but you know, خلاص, you just memorize it. It's a great question anyway. So describe ways to demagnetize a magnet. Same thing as the first question. Heat a magnet to a high temperature. Knock a magnet with a hammer, and place the magnet next to a strong alternating current force. You can see here they didn't choose placing a magnet to a freezer, and the other question they didn't put room temperature and like dry places. So in general, it's fine to store it in any temperature or like in any conditions, provided that you have the iron keeper. So question 4. Which statements are true about an electromagnet? An electromagnet can create stronger fields than most permanent magnets. An electromagnet can be switched on or off, and the strength of the electromagnet can be varied by the electric current carrying through it. This is the advantage. The bottom two, actually, all of them are the advantages of the electromagnet. First and foremost, it can be all switched on and off. Now, let me give you an example of this. In junkyards or wherever they store the trash and the cars, when they put them into like be melted, right, to be recycled, they need to melt the metal and whatever. They use an electromagnet because obviously, how are you gonna lift the car in the first place without a really really strong magnet, right? It's not possible with hands or like at least like one pair. So what they're gonna do, you're gonna get a really strong magnet. Okay, you have the magnet, you have the car up in the sky now, and you're ready to drop it into the pit to like be destroyed and be melted. How would you like go if it wasn't a permanent magnet? How would you like turn the permanent magnet off? Let's see. How would you turn it off if it wasn't an electromagnet? You can't. Yeah, and you can't just break the force between them that easily because it's a very, very, very strong force. So this is the advantage. You can switch the current on and off. Okay. And the strength is common sense. I don't need to explain it. And the strength of an electromagnet can be varied by the electric current through it. Okay, so let's say you want a magnet, right? You want a magnet, and but you don't want to use it to its full ability because maybe you'd waste some of the properties. I don't know. You'd logically like not set it to the max because you don't need to. You don't want to waste as much power as you need to, right? Because you don't want to waste electricity. So you'd set it to like a medium, a medium usage, so it's just appropriate enough to lift the object. So that's another advantage of it. Okay, question 5. The diagram below shows the cross section of a wire and the 4 points towards it. Now, keep in mind this is cutting away from the viewer and it's into the plane, right? So you apply the right hand rule. Now, I can't show you how to apply the right hand rule, but basically, you get your thumb in the direction of the current and you get your curled finger and you uncurl them, like you begin curling them, like you lift your hand and then just go in a curled position. And that is the arrow, and that is the direction of the uh, magnetic field. Now, I can't really explain this to you because I'm not like with you guys, and I don't have a camera. By the way, face reveal soon, hopefully. Even though most of you already like know how I look. Whatever. Besides the point. So the way it turns is according to the right hand rule, and I believe it's called Maxwell's screw rule, but just call it the right hand rule. Okay, I explained this in another video. So I have a tip, and it's very, very useful for this one. So where is open board? Okay. Basically, if you think about it, right? First, you draw out the field. Let's draw out the field. So it goes like this: north to south, always north to south. Okay? Now, the easiest way for me to memorize this, and the easiest way, arguably, for anyone to ever memorize this, is that the direction at the poles is always gonna be the opposite in the direction around the poles. So, like, the point, let's say here is, or actually, do it for me. Why am I doing this? So, here, the direction of B, so like B is gonna be rightwards, right? Because A is gonna be in the direction of the of the field. Anyway, it still follows the direction of the field because as you can see here, the field goes to the right at B, then it curves to the left. But you know, to make it easier, because some people might not understand it like that, you can see at A it's going to the left, right? So at B it's gonna go towards the right, and the other way around. At B it's going to the right, so at A it is going to the left. Okay, so basically they're just opposites. And it depends on what they give you. So we're just gonna apply this. The magnetic field at point A is directed leftward because again it follows the field. See, it's going to the left. Okay. The magnetic field at point B is directed rightwards. As I said, it's opposite. They're opposite. So if this one goes left, this one goes right. Perfect. Okay. So three or C, sorry. The magnetic field at C is leftwards. Again, it's also opposite at the pole of the pole at B and D. And D, it is rightwards. I just said the reason three times now. I'm not going to say it again. There's no need to. The magnetic field created by the solenoid at point A is directed rightwards. Okay, now this one's another right-hand rule. But basically, uh, this one, you find the current instead of you have the current given to you. So what you do the opposite of the first rule. You get your curled fingers, you open your hand, curled fingers as in your every hand other than your thumb, right? Then you curl your fingers in the direction of the arrows, so like this. So you begin curling it from the up to down. You'll get your thumb pointing to the right. So A is gonna go like this. This is the current I. If you try it, like or you open your hand, you curl your fingers in the direction of the thumb of the arrow. Sorry, you'll get your thumb pointing to the right side. Okay, obviously on your right hand. Now, this also, for example, if you had this where it was going up, so I'll just draw like this, even though it's a very bad drawing. It's meant to loop around, but whatever. Here, if you were to do it, you open your and curl your fingers in the direction of the up arrows, you would see that the current goes left. Or so you're like this. This would be the direction of I. That's it. Now, it would be much clearer if the way I could explain to you if I was like on a camera, but sadly not. So can't do that. Question 8. Iron fillings are used to draw maps of the magnetic field by sparkling them around the magnet. Now, these maps are called flux patterns. Now, you guys should know this is grade 6 science, but if you guys don't know, you memorize it. I don't. There's nothing really to explain. The iron fillings show the line of action of fields as curved lines. No, they do not show the actual sense of the field lines. What they mean is basically, so say you have iron fillings here, right? Like I'm gonna draw it kind of, you know, these are all iron fillings. Okay, like this. Now, if I gave you this, if I were to give you this drawing, right? Could you tell me which pole was the N and the S? You couldn't because it's non-directional. It doesn't show. It shows the line. It shows that it acts like this, right? It shows that it's acting in this way, but it doesn't show if it's acting to the left, so like this, or to the right, so like this. It doesn't show that, so we don't know where is the pole. So it doesn't show the sense of the field. It just shows the line of action. It just shows you from it is going from where to where, not directionally. It just shows you like the lines in general. Okay, this one we're gonna use the process of elimination. First of all, let's draw out the normal pattern of a bar magnet and S. Right, it will go like this, and it will go like this. So like this. Okay, this is just a simplified drawing. Obviously, we can add the lines like these. Okay, now, which sketch shows the correct flux pattern of a single bar magnet? Okay, now, we know that it leaves the N and enters the S. This here, it's entering the N and leaving the S. So it does this, the first one's wrong, right? We cross it out. Okay, this one is leaving the N, so this part is correct. However, this one's also leaving the S. This is wrong here, right here. It should be entering, should be like this. So this is also wrong. That leaves us with these two. Tamam. So Here it's leaving the N, okay, entering the S. Correct. So far, correct. Now, however, if you notice around the flux lines, it is going from S to N. Like it's going from S, starting at S, leaving at N. This is wrong. It should be going the other way around. So this is wrong. This is also option 4. Now let's check option 4. Maybe we made a mistake while checking. It leaves the N correctly. It enters the S correctly. It is going from N to S around the bar. So yes, this is also correct, meaning option 4 is the correct answer. Okay, question 11. The two magnets are placed side by side with their like poles together as shown in the diagram below. They repel each other. Select the point where the repulsive force is strongest. Now, honestly, this is common sense because if you think about it, like you might be asking why is it not to the poles? Because there are 2 points at the poles first of all, so this wouldn't really make sense. So like straight away, first of all, let's eliminate this. These two are outside of the magnet, so they're gonna be very weak, right? Now here you're gonna have the force of repulsion, the action force of both the poles, of this pole here and this pole here. Now I'm not gonna draw it accurately because I'm not Picasso, but it kind of makes sense, right? It does make sense. So kind of, you have the combined repulsive force on both sides. This is where it will be the strongest. Here you have the repulsive force of the N pole only, and here you have the repulsive force of the S pole only. Here it's combined, so these two are also not the strongest. They're strong, they're very strong, but it's not the strongest. Okay. Which statements are true about magnetic shielding? Soft iron is used to transfer and divert a magnetic field. Magnetic shielding is attained by shunting fields into iron. And that magnetic shielding provides sensitive devices, protects sensitive devices from external external fields. Okay. So, question 13. This is, or actually, let's explain this. It's fine. Soft iron is used to transfer and divert magnetic field. This one you memorize if you want like further explanation, and I think they only explain 3 lines of it in the book. Read the book. Okay. What did I do now? Whatever. Magnetic shielding is attained by shunting fields into iron. Now, a lot of people don't know what shunting means, and I didn't know until I looked it up like 30 minutes ago. Actually, used to memorize it. Just basically means you forced it in, or like you pushed it into something. Then, magnetic shielding protects sensitive devices from strong external fields. Honestly, I feel like this is very common, like sense, because it's shielding. Obviously, it's gonna protect. It's in the name. This is English. This isn't even physics. A soft plastic rod. Now, plastic's an insulator. Why would it use to protect the? Why would it amplify the strength of a magnetic field? It wouldn't be magnetic anyway. So this is already wrong. The magnetic field is inside an iron, is maximum inside an iron ring. It is not, because then the magnetic shielding wouldn't really make sense then, if you think about it. So the other three, if we go back to them, where am I? If we go to them, yani, you'll see that they are the most logical choice. Okay, question 13. To change the shape of the magnetic field lines of a wire magnet, soft iron can be used. Obviously, soft iron and magnets, basically everything you need to know about magnets, anything can be done with soft iron as far as like I'm concerned, honestly, as long as there are exceptions, which I don't think there are that much, other than maybe the loudspeaker and the current meter or the ammeter, same thing. um I moved back a question. Why did I? Oh yeah, no, I did on purpose. Yeah, okay. Here you can see as well in the other question, soft iron is used to transfer and divert a magnetic field, which is basically what they're saying in this other question here. So the magnetic field of inside the loudspeaker is an axially symmetric radial field. Do you memorize this? And keep in mind the other one, the current meter or the ammeter, is plane symmetric. Okay, this one's axially symmetric. I think they accept axial. Yeah, axial symmetric, and the other one radial. They're both radial, by the way. And the other one is uh, plane symmetric radial field. Okay, which material is not used in the experiment to demonstrate the dependency of electromagnetic force on the direction of the current and the magnetic field? Okay, this is reed switch. By the way, in the quiz, I don't know if this was only me, but I put reed switch. It kept giving me it as like percent 20 or something in between the options. So I don't know if this happened to you too. You're right. It is, the question itself is wrong. I don't know about me. I don't know why it bugged out like that, but it did. So it is the reed switch. They give you rheostat and they give you a lot of other things, and they're all used because a rheostat used to control the current. They also gave you a copper wire. How will you control the current, right? Without the copper wire. They gave you the horseshoe magnet, which you need because it's the magnetic part. Basically, everything in that experiment linked to the words they gave you in the sentence. So you just had to find out which word did not link. Anyways, the point labeled X is a North Pole. Now, how do we know for this question? They're repelling each other. Look, this repels. They're not attracting. Attracting would be like this. This came in the mini mock and it was a past paper material question, by the way. So, you guys should know this. Anyways, so as you can see, it's repelling, right? Because it leaves this neutral point, right? This neutral point means that there's no attractive force going on. So obviously, you see this neutral point, no forces, no magnetic field lines. They repel each other, which means like forces repel. So the North Pole. Okay. They will accept N. I think they accept N. They accept N. Any plotting compass felt at the point 3 will remain its orientation. Obviously, it will because the magnetic plotting compass attracts the magnet depending on the magnetic field. There is no magnetic field at this point. It's nothing. There's nothing there, so it will remain in its position in the way you placed it. Okay, the magnetic field, the iron bar is placed near a permanent bar magnet. The magnetic field is shunted into the iron bar. I explained this like 4 questions ago, basically forced in. I think they even said trapped. Trapped, shunt, trap, whatever. Yeah, okay, all accepted. The strongest magnetic field, obviously, because this is gonna be an attractive force here. This is just gonna attract the magnet or the bar, right? So you're gonna feel the attractive forces here at 4. If you think about it, يعني. Accepted four as letters. Why are they okay? Who's writing four as letters? Whatever. So radial fields are fields that weakens away from the center and remain uniform at constant radius from the center. Okay, you don't really need to know that, but they might ask you it. يعني I highly doubt it, but يلا, it's fine, memorize it. Radial fields are fields which weakens away from the center and remain uniform at a constant radius from the center. Select the thing. Now think about it logically. Radial, so there's a radius, and the only thing that has a radius, as far as we learned, is a circle. So it's going to be something circular. Okay. Now I'm not sure if they're going to ask about the upper armatures and the lower armatures of the speaker. They shouldn't. Hopefully they should. Let's go over them. They're not on this quiz. Such magnetic fields can be used in loudspeakers. We said it before. Radially symmetric in the loudspeaker, plane symmetric in the current meter or the ammeter. Okay, question 20. Uh, Again, right hand rule here. I can't, you know, I can't show you how to do this. I need a camera, which is something I don't have. Now, right hand grip rule is the one for the solenoid and the curve. The one that we saw, the one that wraps around like this, and then it does the arrow thing. Whatever. I'm not good at drawing it. Maxwell's screw rule is this one. This is the right hand rule of this one. It is this to get this. Now I showed you how to, I explained how very briefly. Ask your teacher about it if you don't understand. I can't really explain it to you. Yani there's nothing more I could do. The end of the solenoid that the student observes is the south pole. Okay, when the student looks at the end of the solenoid, she notices that the current in the loops flows clockwise. This question is again right hand rule. The whole thing is the right hand rule. If you were to apply it, you'd find the south pole. It is in the south pole, and the magnetic field is directed away from the student. Okay, question 21. Now, this one. Okay, this one has a formula. We took it today, but it was briefly covered in chapter 3 like a week ago. So on Wednesday. It is phi, so I'm just going to draw phi out, equals to, what was it? IBL cosine alpha. Okay, so uh, you know that, like, let's if we were to put it on a calculator. So let me open the calculator. Where is Casio? Casio's up. Here. Okay, if you were to put on a calculator, so just so you guys, need to get you started with this, to get you familiarized on why. Cosine 90, just to show you, even though you should know it, is 0. Okay, so, oh wait, no, wait, this is sine alpha, not cosine alpha, my bad. It is sine alpha, that's why. Okay, so my bad, slight miscalculation. Sine 90 gives you 1, so it was supposed to give you 1. There we go. So you know that then at that point, at this point here, when alpha equals to 90 degrees, you will have the maximal, like, what can I say? Maximal phi, which is the flux. Phi is the flux. So I'll write it down. Phi equals flux. because you're multiplying this by 1. Meanwhile, if you were to do it on, like, for example, sine 50 or 75, let's say, or خلاص 50, you'll get some 0.7. So you multiply this result by 0.7, which reduces your answer. It makes it smaller. So at 90, when it's perpendicular, you get the most flux. So, sorry, a bit sick. Let's start doing this now. Okay. So obviously, they said label the one with the smallest flux as 1. So what we're gonna do, we're gonna start off by labeling the one with the strongest flux, which is the one that goes to 90 degrees, which is this one, as 4. Obviously, since it is maximal when it is 90, and you can see here, like, imagine this is a normal here, like this, it makes 90. So, I really need to explain this, but it's perpendicular. When it's perpendicular, which is 90, you will get the maximal, and hence why it is 4. Okay. Now, at the same time, this is gonna be 0 degrees. So, let's put it on the thing. Sine 0 gives you 0, right? So this is gonna be the 1, because whatever the phi value was, right? F, or fi, I b l sine 0 will give me 0. So this whole thing, phi equals to 0. So there's no point in doing this. My handset is the weakest. You don't need the calculation part of it, by the way. You need to know is the angle and its orientation and everything. Okay. Now, you can see for these two, this one's going to be a bit tricky if like you were going based off the angles alone without like the calculations, without actually looking. You see that it's going this way, right? That means the flux is traveling in this direction. Here, even if actually you don't even need to know this, whatever. You can see here like more flux passes through here fully and here a lot, right? Here it stopped, right? However, here barely anything can pass through, only like at the edges, which means like compare the red line here to the red line here. The red line here is much bigger than here, meaning that more flux can or sorry, yeah, more flux can pass through, and we want the flux to hit, right? We want the flux here. We don't want it on the surroundings. It's useless. So basically, that is why we put this as 2, since it can let the most pass through. It can let more than this pass through, since this is 3. خلاص, that's it. Question 22, which is the last question. Okay. Select the pictures in the magnetic electromagnetic forces the same direction. Okay. So let me start by explaining why it is these two. You see here N and S into the plane, right? Now, if you reversed it out of the plane, to have the same direction, you're gonna have to reverse the poles. So the S will be the N and the N will be the S. And as you can see here, this is what they did. They reversed this, and this was into the plane. They made it here I out of the plane, right? Which means the only way for it to be the same is you have to reverse the poles. Hence, the S at the N position initially here, and the old S became N. Basically, you flip the field, be it into the plane or out of the plane. It will be um, it will be changed. It will be changed as long as you don't put it in the if you don't flip the poles. If you flip the poles, you will have the same electromagnetic force. The current carrying rod in the diagram below has been moved closer. Okay, U-shaped magnets. U-shaped magnets on the inside here. Let's just make it bigger. SN, for example, or let's draw it accurately to their standards. So N here, S here. Inside it is uniform. It will always be uniform. Doesn't matter wherever you put it, right? Here it is just being moved closer. However, it is a U-shaped magnet, so it is still uniform. It is still a uniform field. So the force will remain the same, right? No matter where you put it. If you put it outside, like if you moved it here, okay, that's a different story. But however, you're inside the thing, you're inside the gap, which still doesn't change it. That's it. Okay, so that was the end of the quiz. If you have any questions, feel free to comment below. I will try my best to answer them. And before I go, since I've been called to say this, shout out to Hassan and Ra'ad. Yalla, bye bye, guys.